Okay, in this video I'm going to solve the first problem on the test. In that particular problem, I provided to you a Word document that you were asked to copy and paste the inputs, and that needs to be copied and pasted into a Vapor Power test app with the substance being phase change material. And so again, as we've done many times, the I/O panel, then I need to go to my Word document. And again, this is the Word document that was supplied to you. One just copies the states, the 11 states, as well as the 7 devices. Again, copy, paste, and load. Okay, upon doing that, my states are all loaded, and we can take a look at what the states provide to us. Now, what we want to do is we want to take a look at the document, or at the schematic associated with this particular problem. And, oops, that's the wrong one. That's the wrong one. That's the wrong one. Okay, let me find this. Well, okay, hold on a second. Back. This is a schematic of the problem. As you take a look at the inputs, you were provided with conditions for the steam at state point 1, and you were told, or when you observe the other state points, you find that 20% of the flow rate, there's 25 kilograms per second at this point, at point 1, 20% of it, or 5 kilograms per second, are extracted off through this expansion valve. Then that means that the 20 kilograms move on through state 3, and then the problem states that an additional 60% is extracted off at state 5, and that 60% corresponds to 15 kilograms per second. The remaining 5 kilograms per second then pass on through the turbine and come out at state 6. That 5 kilograms then is in the condenser. It's then pumped to the mixing chamber. The 5 kilograms per second that was extracted off at 2 gets expanded through a valve into the process heater. The process heater is operating at a pressure of the extracted 15 kilograms per second. So what happens here is 20 kilograms per second go through the process heater and come out at state 7, and that is then pumped up to the mixing chamber pressure. Now, the mixing chamber pressure is the pressure, the initial pressure. So the condenser, the pressure of the condenser is given, and that 5 kilograms per second is pumped up to that same pressure. So the 20 and the 25 then mix to form the 20 and the 5 mix to form the 25 that then go to the boiler. So in this particular problem, what you're asked to do after bringing in all of the information, a device 3 has not been obtained or has not been written, and so you are to make a device 3 that corresponds to the mixing chamber, and that will be a mixing, multi-fluid mixing type of heater. 10 and 9 will be coming in and leaving at 11, and so we need to do that particular device. And then you were asked to make this turbine, instead of isentropic, you were asked to make this turbine a real turbine with an 85% efficiency associated with each stage. And so in that regard, I've asked you to obtain a real state 15 and a real state 16. And so as you can see here, you see that add a state 15 that replaces state 5 and a state 16 that replaces a state 6. And so what's going to happen is 15 and 16 are going to be the new real state associated with the extracted fluid and the final fluid going into the condenser. And therefore, those particular device panels also need to be modified once one determines what the real state is here and the real state is here. Now, one of the things that you need to keep in mind is that whenever we look at an irreversibility associated with a turbine, we calculate the isentropic condition, and in that case it's going to be state 5, and then we modify and generate a state 15 that takes the isentropic work and multiplies it by 0.85 and adds that enthalpy to the incoming. And so the enthalpy associated with state 15 is a little bit higher because there's less work being generated. Now, with that in mind, one has to keep in mind that that's the true state going through the second stage of the turbine. And so when one goes through the second stage of the turbine, the state 6 is going to be the isentropic condition. And so that isentropic condition at state 6 is going to be, if we were to do it technically correct, that state 6 is going to be the isentropic value associated with the fluid, the real fluid coming out of here, which has an entropy associated with it. And state 6 will be that isentropic condition based on that a little bit different entropy. And so this stage here, if you think about this second stage acting on its own, the nuance that we have to kind of understand is what actually goes into that stage is a fluid at condition 15. And then we're treating that second stage as isentropically going to state 6 and then actually going to state 16. And so that's going to be what we need to keep in mind. So let's go ahead. I've taken the information out of the Word document, and that information out of the Word document now has been entered in to the software, and so one can then start to see the various states that have been already established. State 1 is the high pressure, high temperature. State 2 is the same conditions. Okay, it's just what is being diverted off, and what you see, the difference between 1 and 2, 1 has a flow rate that's equal to 25 kilograms per second. 2 is the exact same thermodynamic conditions, however, it's 20%. The m dot is 20%, which is 5 kilograms per second. And then the remainder, which is m dot 1 minus m dot 2, which is 5 minus 25, which is 20, the 80% of that original 25, it moves on, and again, it has the same conditions. And so state 1, state 2, and state 3 have the same thermodynamic conditions. The only difference is they have different mass flow rates. And so now we're ready. As you can see right now, state 4 is what comes out of the expansion valve. And so state 4, it's been stated that state 4 is operating at 600 kPa, which was the extraction point of the turbine. And so state 4 is an isenthalpic expansion, and so the enthalpy stays the same. The mass flow rate is m.2, which is the 5 kilograms per second. So that's state 4. State 5 now is going to that pressure, that P4 extraction pressure. And what we know about state 5 has an entropy associated with the incoming entropy. So this is the isentropic condition. Okay, if we had a perfect turbine. And so then what happens is state 5, if it was a perfect turbine, the conditions at state 5, which we see here, have certain properties associated with them. They then expand to state 6 with the same entropy as at state 5. And so the second part of the turbine isentropically goes down to the lowest pressure in the system, which is 9 kPa. And so between 5 and 6 then is that particular isentropic expansion. Now we're going to modify that in just a second. And then we go into the condenser. The condenser operates at state point, this state 7 is what's coming out of the process heater. And what's coming out of the process heater is at state 4, or at pressure 4, which was the extraction point. And it was stated in the information that it comes out at the saturated liquid condition. So that's what's going to pump 2. State 8 then is what's coming out of the condenser. And it's coming out at the pressure of the condenser, which is state 6, as a saturated liquid. And so that's a standard. The m dot there is the m dot at state 6, which is just the remaining 5 kilogram per second. And then that then goes into the pump, and the pump brings everything up to the high pressure in the system isentropically. And so S8 is equal to S9, and the m dot is m dot 6, which is the 5 kilogram per second. Now state 10 is coming out of the pump from the process heater, and it's also bringing up that amount of fluid, that 20 kilograms per second of fluid that came together in the process heater, bringing it up to the high pressure of the system. The m.7 is the combined amount of that fluid, and that corresponds to the 20 kilograms per second. And again, that particular pump is isentropic. And so that gets us state 10. And then state 11 will be calculated once we put in a device panel associated with the mixing chamber. So the first thing we should do is go over to the device panel. And the first device panel that you see here is the device panel that corresponds to the isentropic turbine. So we see state 3 coming in, which has state 3 coming in, which has 80% of the fluid, and then state 5 coming out, which is 60% of the fluid, and state 6, which is the remaining 20% of the fluid. So what's going through this turbine is just 20 kilograms per second, with 15 coming here and an additional 5 going out. And so this then represents the isentropic turbine, and we see how much work it generates. State 2 then is, as you can see, 4, 5, and 7. And 4, 5, and 7 corresponds to the process heater. We have 4 coming in, which is 5 kilograms per second. We have 5 coming in, which is 15. And we have 7 coming in out, which is 20. And so this is what's happening in that process heater. Okay. And so in this particular process heater, there is no work being done, but there is heat transfer. Okay, and we see how much heat transfer is pulled away in the process heater itself. Okay, then we can go to device 3, which we need to add. And so device 3 is going to be the mixing chamber. And the mixing chamber is an open device. It's already set up for a multi-mixing. It's an open device that's bringing in 10, state 10, and it's bringing in state 9. And so those are the two streams coming in from the 2 pumps. And they come out then with 11, which is the final state. And so that type of a mixing system has no heat transfer and no work. And so if I hit super calculate at this particular point, okay, and then I go back, I go back to the device panel, now you'll see that all of the properties have been determined. And so now we have put in the proper device panel for the mixing chamber. If we keep looking at the other devices, 6 to 8 is the condenser, and this is how much heat is being rejected by the condenser. Device 5 is from 7 to 10, and that is one of the pumps. That's pump number 2. And device 6 is 8 to 9. That's pump number 1. And you see how much work it's requiring. And then finally, device 7 is 11 to 1, and that's the boiler. The boiler is supplying 79 megawatts of heat. And so device 7, there are no other devices. And so we have all the devices in there. Okay. So what we need to do, though, is we now need to go and add some additional states. And as I said, one of the states that we're going to add is state 15. And state 15 is going to have the conditions. That is the actual output for the isentropic stage. And so what we know about that is the pressure there is the same as pressure 5. Okay, it's expanding to the same pressure. It no longer is isentropic. We do know that the m dot is equal to the same m dot 5. Okay, and that ended up being 15 kilograms per second is what we're taking out there. But now what we have to do is we have to add the value of the enthalpy at that point is the value of what came in, which is H3, minus then the isentropic work, which is H3 minus H5 times 0.85. And so this enthalpy, oops, I forgot that was, oops, right here. That's a times. That's a minus sign. Okay, so that's how we handle an isentropic efficiency of a stage of the turbine. Again, it starts at a high level. This H3 minus H5 is the isentropic work, and we take 85% of that and subtract it from the higher value. And so that's our state 15. Now we're ready for state 16. And what we know about state 16 is that we have a pressure that is the same as pressure 6. Our m dot is the same as the m dot that we developed for 6. And we have to do the same thing now for the enthalpy. Now the enthalpy at 16 is starting at H15. Okay, now that's a crucial piece of information. It's starting as if it was its stage of its own with an actual enthalpy coming in, a real fluid that is at that level because of its irreversibilities. And so then we subtract the isentropic condition. Now the isentropic condition is going to be equal to H15 minus H6, okay? And H6 is the isentropic value associated with the isentropic expansion in that second part of the turbine times 0.85. Okay, so basically it's what's coming in, what the isentropic condition is coming out, times then 85% of that isentropic work. Now, putting that in, again, we have to say, have we calculated state 6 correctly? And so the answer is no, we haven't. And so we need to go back to state 6. And again, state 6 represents the isentropic expansion now from 15 down to this state 5, or down to this state 6, or this pressure at 6. And so we need to change this entropy to S15, okay, because it's actually starting at the state 15 and it's going through isentropically to 9 kPa. And so now we have the correct state for 15, and we have the correct state for 16. And again, because of the irreversibilities of the two turbines. Now, the last thing that we have to do is go back to our device panel, and the one in particular that we have to change is the turbine itself. And so we know that what's coming into the turbine is state 3, and then what is being extracted off is actually at state 15. And what is also then taken off at the end is at state 16. And so that's our new turbine. And as you can see, this external work dropped from 20 megawatts to 17 megawatts because of the irreversibility of the real turbine. Now, is there anything else we have to look at? Well, we have to go back and we have to re-look at this particular process heater. And so what's coming into the process heater is actually state 15 instead of state 5. Okay, 4 comes in from the expansion valve and 7 comes out of the process heater. So we had to make that change. And then we look and we see everything else is okay. It was just, we have to look at the condenser. So where is the condenser? The condenser was the 6 to 8. And this 6 is really now 16. And so this is the real condenser. And so now we have 16 to 8 as the real condenser. And so with that in mind, we now have obtained all the proper states, and we've also included all the proper devices, and we can go and take a look at the cycle panel. And in the cycle panel then, shows us that for this particular case, the first law efficiency of this particular process, here's the heat transfer in at the boiler, and this is the net work. And the net work is associated with the 2 stages of the turbine minus the work associated with the 2 pumps. And so this is our net work, and this is the amount of heat transfer in. And so the strict definition of the thermal efficiency, it's 21.45%. But as we saw before, when we had a cogeneration type of plant where the process heater is generating some heat that we're using, our numerator of our thermal efficiency would be modified with that additional heat transfer term. Okay, so the problem continues asking you to calculate the second law efficiency of the mixing chamber and the process heater, as well as the regeneration plant in general. So the second law efficiency that's given in this cycle panel is the answer to the cogenerations plant general overall second efficiency, second law efficiency. So we still have to go to our I/O panel and make a couple of calculations. And these calculations are going to be for the process heater and for the mixing chamber. And so we're dealing with size, which are the flow exergies, and each of them have an m dot associated with them. And so the process heater has two streams coming in that form a single stream going out. And so the eta, let's call it the eta of the process heater. Okay, eta process heater is going to be, in the numerator, is going to be what comes out, which is m dot 7 times the psi value at state 7. Okay, so that's the flowing exergy coming out of that process heater. And we divide that by the m dot 4, which is what is coming from the expansion valve at its value of psi, plus what is coming in state 5. Now that 5 is actually 15. It's m dot 15 times the psi associated with that state 15. And so what we have in the numerator is the exergy, the flow exergy coming out, and in the denominator we have the two streams that are bringing in exergy. And so we see that the second law efficiency associated with exergy for the process heater is only about 10%. Now we want to do the same thing for the mixing chamber. And for the mixing chamber, we'll call that eta, and we'll call it MC for mixing chamber. And what we have there is we have two streams coming in and one stream going out. And so we have the same thing that we really had over here. And so I'm going to copy, just to speed things up, I'm going to copy this here. I'm going to put that into here, paste it. And so what I said, the two streams were 9 and 10. And so we have a psi, we have an m dot 9 and a psi 9. Whoops, I'm sorry. We have the output first, which is 11 and 11. So that's what's coming out. That's the exergy coming out of that mixing chamber. And that's due to mass flow at 9 with its exergy and mass flow at 10 and its exergy. So in this case, the denominator is the two streams of exergy coming in. And hopefully we would like all of that exergy to be picked up by the outgoing stream 11. And what we see under this particular case, I made a mistake, and this psi 1 should actually be psi 11. And so I'm going to put that in. And as you can see, I immediately knew that there was a mistake because the value was so small. And so now we have state 11 in the numerator. That's what's coming out. And then we have the combination of 9 and 10 going in. And so that mixing chamber is about 90% efficient on a first law basis. The reason why the process heater was not as efficient in terms of flowing exergy is because most of the exergy in that process heater came out in the form of heat or energy that was brought out of the process heater. And so when we just looked at flowing exergy of the steam, we only retained about 10% of the flowing exergy, keeping in mind that a lot of exergy might not have been destroyed. It might have just been transferred out of that process heater. And so that then is the answer for that particular problem. So, okay.